Hey everybody, today I'm going to be talking about Kubernetes. If you already know how Kubernetes works and you just came here to learn about monitoring pods with ExtraHop, feel free to click the link in the upper right hand corner right now, but for anyone else who might be unfamiliar or just wants a refresher, let's get into it. At its core, the purpose of Kubernetes is to run applications, and the simplest way to do this is just to run the app in a computer. But with lots of apps, running each on its own physical machine will quickly land you overrun with physical hardware, much of which is unnecessary. To better utilize your hardware, you could start running more than one app on the same machine. But as your apps grow, you will likely discover that some of them are eating up more than their fair share of resources, which leads to performance degradation for your smaller apps. You need help. You need virtualization. By running apps on virtual machines, you can conserve physical hardware while limiting apps from growing too large. Great, but you're still wasting a lot of valuable resources by maintaining separate operating systems for each VM. A better solution is to place your apps inside of containers, which are able to share operating systems and other system resources, rather than duplicating those over and over. But that's far from the only advantage. By storing containers in a centralized repository, you can make it easy for machines to pull down copies of the container to run apps wherever they're needed. Kubernetes provides a framework for managing containers to provide seamless access to applications. Let's take a look at how that works. In Kubernetes, containers are grouped into pods, which can include one or more containers. These pods are often duplicated to create what's known as a replica set. The replica set is exposed to the network via a service. A network service is an application, such as a website or DNS, that clients can access over the network. And when these services are backed by Kubernetes pods, clients can access them without ever having to worry about which pod they're actually talking to. That's the magic of Kubernetes. But it doesn't stop there. When a pod starts to fail, Kubernetes will automatically take that pod offline and prevent clients from accessing it. After that, Kubernetes will spin up a new pod and will begin routing clients to access the replacement. In Kubernetes, the machines that a pod runs on are referred to as a node. The pods for a service can reside all on the same node, or spread across two nodes, or really spread across any number of nodes that you want. There's no limit to how distributed your service can be, but to a client, it will only appear as one united network service. But how do clients access these services on the network? Well, there are a couple of different ways to set that up. The first is called a cluster IP service, which exposes the service over an internal IP address. Let's take a look at how that works. Assume we've got two nodes on our network, and each node has two pods, and two of these pods are part of a network service. Every Kubernetes pod always gets its own internal IP address, no matter what the setup is. And with a cluster IP service, the service gets its own internal IP address too. So when one of our pods wants to talk to the service, it sends a request to that internal IP address. That request goes through a Kubernetes proxy that runs on each node in the Kubernetes cluster. The proxy then handles routing the request to the service. In our example, the proxy might forward that request onto a pod on the same node, or it could forward the request onto the pod on the other node. That's how a cluster IP service works, but those services are only exposed within the internal network. What if you want the service to be accessible to external clients? For simplicity in this example, each node only has one pod, and both pods are part of a network service. Each node has an external IP address, and each pod has an internal IP address. And the service is assigned a port number. When a client comes in from the outside, the client sends a request to the public IP address of the node, along with the port number of the service. So the request goes first to the node and then to the Kubernetes proxy running on the node. Then, similar to a cluster IP service, the proxy figures out where to forward the request. It can send the request on to the pod in the same node, or it can reroute the request over to the pod on the other node. This is called a node port service. You can also do something similar with a load balancer. For this example, let's say we have a cluster with just one node, and that node has a single pod which supports a network service, and that service is exposed to the outside world via a load balancer, which I realize might not make much sense from an architectural standpoint, but it might make sense if your PowerPoint presentation is running out of room. So the load balancer has an IP address, and the node has an IP address, and the pod has an internal IP address. In this case, the service is exposed by assigning both an address and a port number to the service. The IP address belongs to the load balancer, and the port number identifies the service on the node. So when a client comes in from the outside, it sends a request to that IP address on the load balancer. The load balancer then forwards the request on to the node and specifies the port number of the service. And from there it behaves the same as a node port service. The Kubernetes proxy on the node forwards the request onto the IP address of the pod. Alright, that about does it for Kubernetes. If you want to learn more about Kubernetes, check out the links below. If you want to learn about how you can monitor Kubernetes pods with ExtraHop, check out this video link. Thanks for watching.